I'm hearing some noise.
Hello?
Hello, yeah.
Sorry, I have one question about potential. Hello?
Yes, Christoph, go ahead, please.
Sorry, I just have perhaps a very silly question, but other than silicon nitride, are there some other potential candidates that are basically currently used that could result with the similar quality of results? So are there some other solutions currently considered other than the use of the silicon nitride for the emitters?
Yeah, this is a very complicated, I mean, okay, let's face it. So of course, there are many single photon emitters. If you're speaking about single photon emitter by itself, let's say quantum dots could be very good single photon emitters. But if you after a big goal like quantum computing, you need like 1 million of single photon emitters. With quantum dots, you because of this inhomogeneity in size, they never would be good for this. So, and it should be also a platform where it could create like 1 million elements and all these interferometer waveguides, couplers and things like that. And that reduces the problem to silicon nitride, silicon carbide. And the thing is that there are good single photon emitters in silicon, for example, so-called G centers. But so far they work only at low temperatures. In silicon carbide, there are also good single photon emitters, which operate also at room temperature. But the thing is, all these emitters, they are, when it comes down to creation, they're still controlled by Poissonian process. They're still statistical. It means that you have certain cap on the highest possible yield, let's say around 35%. But that's not really acceptable for this photonic quantum circuitry. So you ideally would like to have yield close to 100%. You need to create these single photon emitters deterministically. And in that regard, the emitters which we obtained in silicon nitride, they clearly are super Poissonian. I mean, by doing nothing so far, we already get this probability to get single photon emitter above 50%. Which indicates, although we don't have proof for that, that by optimizing their creation, we possibly would be able to create them deterministically, meaning that the yield would be close to 100%. So that's about this photonic quantum computers. Of course, they're very different. There are other approaches, it's like on superconductor and qubits. But you see, I mean, photonic quantum computers is different from all others like superconducting or trapped ions in the sense that this approach doesn't require gates. And because in this case, it's so-called one-way quantum computing, and the measurement itself, which is single photon coincidence, serves as a gate. And it's really unique compared to with all other approaches which require gates, logical gates. The problem with quantum computing in general that it's error correction. So basically, if your algorithm requires n qubit, let's say 500 qubits, to control error would require much more qubits, which makes these approaches not scalable, and fault tolerance, it's a really huge problem. With photonic quantum computers, the rate of errors is actually estimated to be 5 orders of magnitude lower. So my feeling that at least in the near term, photonic quantum computing is the most promising one. And the only thing is actually which is needed for photonic quantum computers is good single photon sources, which you could create deterministically. So because all others, these Mach-Zehnt interferometer waveguides, I mean, it's not a problem to make it with platforms like silicon or silicon carbide or silicon nitride. So therefore, we are so much keen on trying to create this deterministically, monolithically embedded single photon emitters. Of course, you could bring single photon emitters, but in this case, you would have big losses. Like if you take single photon emitter and place on your waveguide, you would have huge losses. In this case, you have these emitters right in the material. So when you put all these things together, so you need to have low rate of errors, you need to have fault tolerant computing, you need to have scalable approach. having this monolithically embedded good single photon sources, which could be created deterministically, could be a game changer.
Thank you very much.
And by the way, connecting to this meta business, of course, what we are creating this array of pillars, this is meta surface in the language of Metamaterials. It's basically, moreover, since these emitters exist, as we suspect, at the interface between silicon nitride and silica, where you create the stress when you do this rapid annealing. It's actually 2D array of quantum emitters created by this meta surface based on silicon nitride pillars. So we are very excited by taking these ideas of metamaterials and meta surfaces to entirely new domain, which is quantum, where, I mean, let's face it, right? That's going to change our lives. I mean, quantum communication, computing, that's something which is going to have so dramatic impact on our lives that it's hard to envision at this stage.
Thank you. Do we have more questions from the audience? I'm sorry, I don't see your image. So if you have a question, you can just speak and ask it. So I have a very naive question, Professor Shalaev, when it comes to basically to the all photonic integration of circuits. So for example, when every time you would be using any complicated device which will require few lithography aspects, you can only unfortunately do 2D devices. If one wants to make something very compact and scalable, one opportunity could be to use this 3D printed circuits. There have been a few circuits, but unfortunately, again, it's only polymers, and you can, of course, dope it. You could integrate some quantum source inside. And I was just wondering, what do you think about this approach, which is then basically like almost a polymer based, and where the geometry actually is very open. You can make some stuff very complicated, but from the material aspect, you are limited from the material.
Right, it's a good point, but let me first say, if you would be able to do it with 2D, that's advantage rather than disadvantage, because it's much easier to do. That's what all this nowadays nanoelectronics or silicon nanophotonics is based on. But you're actually also right. Like, for example, if you look at these computers of nowadays, they're not truly 2D already. It's more like a multi-layer structures, because you have actually several layers, like one for memory, with another for processing, another is like optical and so on. That increases functionality. It allows to more closely packed your functional elements by exploring the third dimension. In my opinion, in this case, so if it would be 2D, that's just great because it's easier, but we might have to also explore the third dimension later on. But at this stage, the simpler the better, because we have already enough complexity in terms of controlling these quantum superposition states, cluster states, which is already exceptionally challenging. And having it in 2D version, it's probably easier than without a third dimension. And I'd like to emphasize again that the fact that our emitters seems to be created at the interface, meaning they have one and the same Z coordinate, it's already a big advantage over other single photon emitters, where you have uncertainty in terms of how deep your emitter is sitting. So the higher control you have over your system, the easier to deal with this quantum decoherence problem. So I believe 2D is just great, and we would like to stay with this. But eventually, if we will face a problem to place more elements, we could explore the third dimension. That's what happens with nowadays computing based on hybrid technology, electronics and nanophotonics, silicon nanophotonics. They're already not exactly 2D. There are multi-layered structures in many cases.
Okay, thanks for the answer. Is there any other question from the audience? Seems to be very shy today.
Hello, Mohammed. Can I ask a question?
Yes, Mohammed, please.
Okay. Thanks for this nice talk. So my question is, when you have this quantum emitter in the gap of the nano antenna, like when the gap becomes very small, like do you take care of some effects like quantum effects, like quantum tunneling, or this kind of effects?
That's a good question indeed. So at very small gaps, there's like spill of the wave function. There could be tunneling, there could be quenching, and that's a problem by itself. When you go into extremely small sizes, like all this quantum transport physical problem exciting. So our hope, and so far everything looks promising in that regard, that speed up, this Purcell enhancement based speed up could be so high that it would beat any possible negative processes such as quenching, for example, because quenching also has certain rate. It's basically coupling of dipole weights, it's mirror image. But if outcoupling would be faster, similar to what other decoherence processes, we could outpace this. So there are lots of physics questions to address it. And it's hard to predict everything. And you're absolutely right. There are many physical phenomena which could play a role when you go to extremely small gaps. For example, if you would use HBN or other van der Waals-like materials and place them in the gap, then of course you could expect things like tunneling, this wave function spilling, and many other things, quenching and so on. But again, we hope that the speed up would be so high that you could outpace all these other processes which could play a role.
Thank you.
Thank you, Mohammed. Is there any other question from the audience? I don't see anyone raising his hand, so I would like to conclude and to say thank you very much for this nice presentation, Professor Shalaev. Your presentation was recorded and it will be available in the coming days online on our platform of MetaMAT with a DOI assigned to it. So anyone who found who have learned something particularly interesting from the talk and just cited this talk actually in the next papers. So thank you very much for attending the webinar, and see you next week.